So just to recap, the output of this whole algorithm, the output of this process, is a hierarchical clustering. As I showed you earlier, we have this kind of tree-like structure with words at the leaves of this tree. And each node corresponds to a different cluster. For example, this node would correspond to the two words red and blue, and so on and so on. As I described earlier, these hierarchical clusterings can be described as bit strings, or they can be mapped to a mapping from each word to a bit string. So in this case, for example, red would get the bit string 111, blue would get the bit string 110. So these kind of representations can be extremely useful. It can be very useful to know, for example, that each of these words is in some sense similar. They're in the same cluster, at least if we look at the first several bits. And what I'm going to talk about in the remainder of this lecture is a very effective application of these representations within the context of named entity recognition. This is work by Miller and others, published at NACL in 2004. So let's now describe how this works. So this is the paper. It's called Name Tagging with Word Clusters and Discriminative Training. It's a really wonderful paper, I think, bringing together the ideas from these brown cluster representations in combination with actually the log linear tagging models we saw in the last week of the class. So Miller et al. Motivate their work in the following way. And this is actually an excerpt directly taken from their paper. So they say, they relate this experience where they had actually built a named entity tagger, and they were demonstrating this to a potential user. And actually, this work was done at BBN, a company which developed some of the best named entity, or has developed over the years, some of the best named entity recognition methods. And so they had considerable experience in this domain. And they were saying that, they knew this, the technology performed well in formal evaluations, been applied successfully in several research groups. All it needed was some annotated training examples for it to be trained in a new domain. But nevertheless, it wasn't quite what the user wanted. And the critical problem was this need for annotated training examples. So, as you've probably realized, if we want to apply, or rather we want to develop a named entity recognizer for a new set of entities, say going beyond people, locations, and organizations, then we're going to have to, at least if we use the methods that I've described earlier in this class, we'll have to collect labeled examples where we have sentences with underlying segmentations, underlying markings of the entities. And of course, gathering this kind of annotated training data can be an expensive proposition. The same is true for the parsing problems we've looked at, also for the part of speech tagging problems we've looked at, and actually many other problems in natural language processing. And so Miller et al. Go on to emphasize this point. And so actually the HMM-based technology they had, which is very similar to what we saw in the second week of this class, required roughly 150,000 words of annotated examples, and to get to peak accuracy, maybe about 1 million words. Okay, so a fairly considerable amount of training data. And that's because there are a large number of parameters in these models, and there's always sparse data. There are always words for which you have too little information. So getting more training data is always going to help, and in reality we need quite large amounts of training data for these models to work well. So the annotators that they actually employed might annotate this data at a pretty fast rate, I have to say, around 5,000 words per hour. That's impressive. But nevertheless, annotating this kind of quantity of data might take several days of annotation. And that might be feasible in some cases, but in other cases that may be just simply be too slow, or this may be too expensive. So the key idea in this work was to use the Brown cluster information to significantly reduce the number of labeled examples required to build a named entity classifier. And so Miller et al. Used something very similar to the log linear taggers we've seen in the last week's lectures. So remember, in a log linear tagger, the history is going to be a tuple ti minus 2, or t minus 2 rather, t minus 1. These are the previous two tags, a sentence w1 through wn, and a position I. For example, we could have the history h is equal to, say, determiner nn, the dog laughs 3, signifying that we're tagging word 3 in the sentence, and the previous two tags were determiner and noun. The label, which is y, is going to be some tag. For example, we have y equals verb maybe. And we have a feature vector definition, so we have a set of features fk hy for k equals 1 to d, where d are the number of features. And these are generally questions about the history in conjunction with the label y. So the key insight of this Miller et al. Paper was to include features in a log linear tagger which not only looked at the identity of particular words in the context, but also looked at the cluster identities of the words at the current position and the previous position and the next position. Let me go over this. Actually, we have a list of the features which were used in this work here. So they use features like the tag and the previous tag. So this would be a fairly standard feature, something like the following: fkhy equals 1 if t minus 1 equals nn and y equals vb. And so you would have many features of this form. This would be 0 otherwise, looking at all possible pairs of tags. We have features which look at the tag and the current word. So this would be a feature such as fkhy equals 1 if wi equals laughs and y equals vb, 0 otherwise. And you would have most likely a feature like this for a very large number of combinations of words together with possible tags. They had a feature which looked at the current tag, for example VB, and some spelling features of the word being tagged, maybe whether it's capitalized or whether it has numbers. This is essentially going to look very much like the mapping from words to these rare word features which capture the spelling features of the particular word being tagged. We have features which look at the tag in the previous word and tag in the next word. These are all pretty standard features, exactly the kind of thing we saw in the previous lectures on log linear taggers, so nothing new there. What's new is these new features which look at the Brown clustering information that I was just describing. So what does this mean? This says it's a feature looking at the tag and the pref 8 of the current word. This essentially is going to look at the first 8 bits of those bit string representations that I showed you for Brown clusters. So this might, for example, say fkhy is 1 if the label y is equal to vb and the first 8 bits of wi, that's the word being tagged, is equal to 1011, some 8-bit string. And you would have features like this for all 8-bit strings that are actually seen in your training data in conjunction with all tags. Now remember that given the way Brown clusters work, if we look at the set of words with this particular prefix, we're going to get a cluster of words at a certain level of granularity, at an 8-bit level of granularity. So maybe you'd find, for example, red, blue, green, or some basically related set of words in this cluster, and this feature will fire for all of those words. So we now have features which generalize across multiple words and moreover capture the membership of words in these different clusters. Now in this work they looked at the 8-bit prefix, the 12-bit, the 16-bit and the 20-bit, and so they looked at everything from a fairly coarse level of granularity. At this level you have at most 2 to the 8, which is equal to 256 possible clusters, right the way down to a bit string of length 20, where you have 2 to the 20 possible clusters, which is an enormous number. At this point you've probably almost gotten down to individual words. In addition to looking at the current word, you can look at the bit strings for the previous word, maybe of length 8 or 12 or 16 or 20, or you can look at the bit strings for the next word of 8, length 8 or 12 or 16 or 20. But again, at a high level, the critical idea is we now have features which can look at the bit strings corresponding to words in the context and can thereby generalize across words which occur in the same cluster.